Hi, my name is Brian Fotheringham, and today I'm going to be presenting the paper Blockchain Applications in Smart Grid Review and Frameworks, which was a paper that was first published in IEEE on June 4th, 2019 by Ahmed Musla, Gang Yao, and SM Moyin. The outline of this paper is in four major parts. The first being a blockchain overview and a review of concepts that help in the reader's understanding of blockchain technologies. Second is a survey of industries that are using blockchain right now. The third section is how blockchain can be used in smart grid technologies and the advantages of using blockchain in those areas. And then the fourth section is the drawbacks of blockchain and the outlook and the roadmap of using blockchain in the future. In order to understand how blockchain might be adopted in something like a smart grid, we need to understand what blockchain is and what its advantages are. In the most basic sense, a blockchain is just a chain of blocks that contain some sort of information. Each block computes a hash code for the information stored. How the blocks are connected is that each block contains not only its own hash code, but also the hash code of the previous block. And in this way, the data in each block cannot be changed or altered in any way, because the hash codes for the current block and the previous block have to align. This adds a level of security that other architectures struggle to achieve. Another key aspect of blockchain technology are the system nodes. Now, each node represents a user of that system. Each node holds a copy of the blockchain itself, and in this way provides redundancy that, again, other architectures cannot achieve. In this way, if one user has an issue with connecting to the network, the information is still held because of all the other nodes that are connected to the network. Adding a new block to the blockchain requires verification from all the nodes in the system. So the process goes something like this. A user, whether it's new or a current user, requests a transaction. And examples could be buying a Bitcoin, requesting data from a PLC, or etc. And this transaction request is broadcasted to every single node on the network. Then the nodes validate and verify this transaction based on an algorithm. When the verification is done, then the block is added to the blockchain with its hash and the hash of the previous block. One of the main challenges with this verification process is that hackers could change the info in one block and use a powerful computer to then calculate the new hashes in the entire system, making it seem like the blocks never changed because all the hashes will line up. Now, many processes have been used to try to secure this vulnerability, and we're going to look at three of the major algorithms for consensus that blockchain uses. One is proof of work, which is widely used right now in current blockchain technologies. And two others are proof of stake and proof of authority, which also try to address this issue. Any of these consensus algorithms try to achieve one goal, and that goal is establishing trust between the parties that are transacting on the blockchain. The first consensus algorithm we'll look at is the most widely used algorithm, and this is proof of work. We can see this sort of algorithm used for Ethereum and Bitcoin, where miners are the users that decide on the addition of any new blocks. Now, the miners partake in a puzzle and try to solve the puzzle using their computational power. So when we talk about work, we're actually talking about the computational power that we can see was used to solve the puzzle. And in this way, the work is easily verified, but the puzzle is actually difficult to solve. So this causes a lot of risk avoidance for the blockchain itself, where the large computational power needed to solve the puzzle actually deters any spam or malicious user from faking any of the information or trying to scam in a transaction. The two lesser used consensus algorithms are proof of stake and proof of authority. Proof of stake has promising signs but is not mature enough yet to be used in applications such as Bitcoin. In proof of stake, there are no miners present, but the validation process relies on validators who have a stake in the block creation itself. So anyone who owns a good in the transaction could be a validator of that block. Proof of stake does reduce the energy and time consumed in the consensus process, but this also means potential reduction of security in that verification process. The next algorithm that could be used is proof of authority. In this case, only approved accounts can place new blocks on the chain. This makes it a more centralized architecture for the verification algorithm, but it does have a faster overall consensus process. However, the drawbacks of this is that one of the main advantages of blockchain is its decentralized nature, and so this has not caught on as quickly as some of the other algorithms. Now that we've looked at the major concepts of blockchain, we can understand some of the advantages of using this technology. The first being its decentralized nature. Because every node that's using the blockchain system has a copy of the blockchain, we have achieved resiliency and redundancy for that information. We can also tell that there's transparency in a system like this because every node has a copy of that information. So you can see every transaction that has taken place in that system. Another advantage is time reduction. Because of the trust between parties given by the consensus algorithms, we can take out the intermediaries such as banks or governments that usually overlook and regulate a peer-to-peer market. And finally, we can talk about data integrity or security with the fraud prevention that is given from the hash codes of each block. In this way, no perpetrators can alter any data, or else every node will be able to see the difference in hash codes and be able to point out that attack. Although still in its infancy, blockchain has been adopted for many use cases in a very quick amount of time. The major use case we can think of is cryptocurrency. Cryptos like Bitcoin and Ethereum have harnessed blockchain security to provide platforms for buying and selling using their cryptocurrency. Not only does this provide a government-free way of buying and selling goods, they also use their cryptocurrencies as a reward for keeping the blockchain secure. We can think about proof of work consensus algorithm and how Bitcoin miners earn Bitcoin for securing the nodes in the system. Another interesting use case for blockchain is in humanitarian aid. One of the main challenges with this sort of aid is the lack of security or lack of transparency in how goods and supplies are being delivered to the people in need. In this way, blockchain can create a transparent and secure system for supplies to be delivered to the proper people. Now we can see how blockchain is very useful in providing security and redundancy for multiple industries. This is when the paper starts to focus on how blockchain can be integrated into a smart grid and resolve much of the conflict that this industry is facing today. Some of the major challenges we see in the power grid industry is the ever-increasing use of renewable energy sources and how these energy sources provide a lot of intermittent power when there's a need for stability, or customers are relying on the stability of energy coming into their houses, their businesses. And we also see that the local and decentralized areas of power generation that we see with renewable energy sources cause a need for peer-to-peer marketplaces in a smart grid system. Now, these prosumers and consumers of energy have to rely on communication applications to buy and sell energy, and this is usually very costly with not much security. Knowing the challenges that face the power grid industry with renewable energy sources, we know that blockchain can account for multiple of the solutions needed for this industry. One of the major ones is to provide the communication infrastructure needed for a peer-to-peer platform that is decentralized, much like the renewable energy sources themselves. The second is to be able to establish trust between prosumers and consumers without the need for third-party charges, which end up increasing the price of energy for everyone. Blockchain can use its advantages for all three sectors of the power industry: generation, transmission, and consumption. For power generation, blockchain can allow energy providers to see real-time statuses of the power grid and cut down on costs that might occur from delayed responses for power intermittency. In power transmission, the blockchain will be able to automate and control these decentralized systems of renewable energy and will be able to address the security threats that are seen in your typical centralized transmission centers. Finally, for power consumption, again, this can be able to manage the energy trading between prosumers and consumers, providing security and trust between all parties. Within energy trading, this is where blockchain can really provide security. Blockchain can remove the fraud from peer-to-peer energy trading systems, and also, along with its proof of work consensus algorithms, can also prove the origin of the energy and be implemented to guarantee the trading process. For these peer-to-peer systems, the blocks on the chain can contain records of the units of the generated energy that's flowing through the power grid. And also, it's allowing instantaneous deals between the buyer and owner of this energy. This gives buyers more freedom to choose their energy price for themselves, and it increases the privacy and security for both the buyer and the owner. And they know that they have trust in this peer-to-peer system. Another aspect of the smart grid that blockchain can improve is in regards to electric vehicles. Now, a lot of the issues with electric vehicles come from how they charge. For a power grid, since electric vehicles take a lot of energy to charge and a lot of the charging is uncoordinated, this causes a lot of intermittency in the power grid from overloading. And blockchain can directly address this in a few different ways. One is to run algorithms that monitor the status of the power grid and then allow for the electric vehicles to charge at proper times when the load is a little bit less, so that the supply of energy to the entire grid is stable. But also, it could run an application that finds the nearest charging station with the lowest price with the most supply of energy at that time to reduce the power cost of charging, but also provide security to the system and reduce that peak to average volume of energy that causes instability in a power grid. Another way blockchain could be adopted into smart grid environments is through a microgrid environment. Microgrids focus on distributed energy resources that are decentralized in nature, much like blockchain itself. So it's easy to see how blockchain could provide a similar demand-side management process for peer-to-peer buying and selling of energy that would reduce peak-to-average ratios in the power grid and smooth dips in supply. In this way, the energy would be much more stable, and also costs would be reduced because of no need for an intermediary within these microgrids. Blockchain could also provide distributed computation and data supervision, giving that transparency and also security within the system to be able to see the status of the microgrid and prevent any intermittency that might happen in the grid. Finally, we can talk about decentralization of the medium voltage direct current link control, and we can think about this as grid operators that are much like miners for Bitcoin and Ethereum, where they have shared responsibilities inside the system itself, and so blockchain can provide that level of redundancy and security for MVDC systems. We can see from this paper that blockchain technology is capable of solving many of the issues facing power grid and smart grid environments today. However, there are also drawbacks of using blockchain technology. The two major drawbacks that we'll look at are expense and wastefulness. With expense, we know that consensus algorithms such as proof of work require high computational power to provide the verification of blocks added to the system. Obviously, this increases the expense of some systems in order to achieve the security that blockchain grants. Another reason blockchain can be expensive is because of increasing miner rewards. Ethereum or blockchain miners can increase the amount of rewards they want from being able to secure this sort of system. The second drawback that we'll look at is wastefulness. We know that each node on the system contains a redundant copy of the blockchain itself. Now, this redundancy does provide security, but again, provides for slower transaction times so that the verification process has to go through all the nodes in the system, which can be many. And it also increases the cost because of the fees and the computational power that's needed to run the system in general. We can see that blockchain can address a lot of the segments of a smart grid, whether it's a microgrid or energy trading platforms, but blockchain can also enhance the security of cyber-physical systems in general. Cyber-physical systems have many vulnerabilities and can be attacked with time synchronization attacks, GPS spoofing, denial of service, much like any other system. But one way where blockchain can immediately improve the security of a cyber-physical system is addressing FDI attacks. And FDI attacks are when perpetrators change data within a system or change data within the measurements being read from a system. And so these measurements will be read and an action will be taken on those measurements. And so if it's false data, it can really harm the system or take actions that it shouldn't. And so with blockchain, since all the information in a block is not changeable, it is immutable, this immediately removes the pervasiveness of an FDI attack. Blockchain can also increase the redundancy of the power grid itself, and so it can use meters as nodes in the distributed network, and like within the FDI attack solution, the meter's measurements are the information of the blocks in the chain. And so users then can monitor how the electricity is being used without fear of any manipulation at all. And finally, we can look at the smart contracts that are used in blockchain technology to enhance the resiliency and be able to secure the transactive energy applications that would provide for peer-to-peer interaction. To summarize, I've presented the Blockchain Application in Smart Grid Review and Frameworks paper published in IEEE by Ahmed Musla, Gang Yao, and SM Moyin. In this presentation, we've looked at how the paper overviews blockchain technology and concepts, what industries blockchain has been used to innovate, and also how smart grid environments can use blockchain to increase security, increase reliability, and provide a peer-to-peer marketplace to reduce costs for all who need to trade energy.